Hello everybody, my name is Enrico Saccon, and today I'm going to present the work titled Adaptive and Scalable Knowledge Management for Robotic Applications via Logic Language. So the problem that we want to tackle is how to create and maintain knowledge bases for robots in order for them to take autonomous decisions. For that reason, we want our knowledge base to be usable and reusable, in the sense that we don't want to create the knowledge base every time, but we want the robot to be able to reuse it whenever it is faced with a task that it already accomplished. We want it also to be understandable and explainable so that we can understand why a robot took a certain decision. And we want it to be scalable so that it doesn't have to consider the whole knowledge base every time, but it can extract the portion it is interested in. And since we want it to be understandable and explainable, then it must also be shareable with humans. So we propose this framework that is divided in 4 modules: a knowledge management system module, a planner, an execution module, and a monitoring module. In the knowledge management system, we use large language models to create a knowledge base written in Prolog. We chose Prolog because due to its inference capabilities and also its natural explainability that comes with logic formalisms. You can see that we divided the large language model in 2 levels: a high level, which captures more general information about the environment and the actions that the agents can carry out, and a lower level large language model, which takes the knowledge base from the high level and more in-depth information about the agents and the environment in order to create a more precise knowledge base. We check its consistency, and if it's consistent, then we use the planner to first extract a total order temporal plan. We then refine it into a partial order plan by extracting its achievers and resources, and then we set up a mixed integer linear problem in order to optimize the actions of each agent based on the achievers and the resources. Finally, we extract a behavior tree, which is a formalism that can be directly executed by the robot, and the monitoring module will overlook the execution and provide new inputs to the knowledge management system in order to update the knowledge base. In recent years, there have been a lot of work with large language models for planning, but they either use them as oracles to provide a plan without taking into consideration any theory behind planning, or they do not consider possible temporal causality, nor multiple robots in the same environment. So here we have a brief example of how our framework works. We provide a natural language description of the environment and the task that we want to accomplish. We give it to the large language model, which provides us with a response. And if it is correct, then that's fine, we have our knowledge base. Otherwise, if it is wrong, we have to fix it. And for doing that, we have some guidelines that may help the user in fixing the errors. Once we have our knowledge base, then we go to planning. As you can see here, we first extract our total order plan. Then we extract the achievers, that is those actions that are fundamental for other actions in order to be executed. And we also extract the resources, which are, for example, some agents that can carry out the tasks. In this case, we can see that we have 3 rovers, so we have 3 autonomous agents that can move at the same time. Finally, we set up a mixed integer linear problem given the resources and the achievers, and we optimize in order to to minimize the make span of the plan. We then extract a behavior tree, which can be directly executed. As future work, we can implement probabilistic and non-probabilistic versions, since we are using Prolog and it comes with probabilistic and non-probabilistic extensions, and this would allow us to capture the uncertainty of the environment. Since we are doing temporal plan, then we have to estimate the duration of the actions, and this could be done using machine learning, or we could integrate task and motion planning to better identify the duration of the actions and also identify its feasibility. Finally, since LLMs may provide some errors, we could automate an error loop where we detect and correct the large language model outputs. Thank you very much for your attention.